These are the nature of science slides. We started off by talking about the difference between a theory and a law by watching this movie. Now, the examples that are used are the Newton's universal law of gravitation and Einstein's general theory of relativity. So, a law is just something that we've never not seen happen. So Newton says that mass is always attract mass. We've never not seen that happen. Now a theory tries to explain why. So these are the difference. A scientific law is a description of an observed phenomenon and tries to predict what will happen. And a scientific theory is an explanation of an observed phenomenon and tries to explain why something happens. So, one of the questions is how many observations does it take for a scientific theory or law to be modified or abandoned? So, all theories and laws are tentative. Newton's law of gravity was eventually supplanted by Einstein's general theory of relativity. Now, why? Because all it takes is one observation or one failed prediction to require that a scientific theory or law be modified or abandoned. So, think about that orbit of Mercury. It arrived half a second earlier than predicted, and Newton's theory could not account for it. So that quote over there by Richard Feynman is, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiment, it's wrong. So then we learned about the scientific method. Now, Galileo came along and refined the scientific method and simplified it into simple steps. Recognize a problem, make a hypothesis or an educated guess, make predictions based upon hypothesis, perform experiments to test predictions, and formulate a general rule. So, a hypothesis is an educated guess to explain an observed phenomenon or fact. Now, the attributes of a good hypothesis are: a good hypothesis should be stated in the language of mathematics. With mathematics, there is no ambiguity, should explain a wide array of observations related to that phenomenon, and should have a test for wrongness. So, when setting up an experiment, there are going to be different variables. So let's take a look at variables when conducting an experiment. So if this claim is made, spinning a penny on the table will cause it to land heads up more than if the penny was flipped. Now, is this a scientific claim? Why or why not? Well, the answer is yes, it is a scientific claim because there is a test for wrongness. Now, the variables are going to be the independent variable, the dependent variable, and the constant variable. So let's look at this problem or this phenomenon that we see and identify these variables. So the independent variable is what is being tested. It's the cause. It's the quantity that is being manipulated by you. It's the quantity that you are changing. There can only be one independent variable for each experiment. Now, the example, do the actions of flipping and spinning a penny affect the percentages of which side the penny lands? The independent variable is what is being done to the penny. Are we flipping it or are we spinning it? That's what we are changing. It's what we are testing. Now, the dependent variable, this is the variable that responds to the changes made to the independent variable. It's what is being measured as the result of the change you make to the independent variable. And like the independent variable, there can only be one dependent variable. So the example, do the actions of flipping and spinning a penny affect the percentages of which side it lands? Well, the dependent variable is going to be the percentage of landing on each side of the coin. That's what we are measuring. Now, yeah, this is what we're measuring. We're changing what is being done to the penny. That's the independent variable to see if it influences the percentage of which side it lands. That's the dependent variable. Now, the last kind of variables are going to be the constant variables. It's what is kept constant and kept from changing when the independent variable is changed. Now, if these are not kept fixed, they could possibly affect the results of the dependent variable. There are usually many constant variables. So, the example, do the actions of flipping and spinning a penny affect the percentages of which side the penny lands? What are some constant variables? Well, the person flipping the penny. Everyone flips a penny differently. The height the penny is flipped, the side facing up at the beginning, whether it's flipped at the end or not, and the penny, keep the penny the same. Lots of variables need to remain constant for this experiment. So this video shows the Mythbusters testing to see whether having a car with the texture of a golf ball will get better gas mileage. So the question is, does giving the car the surface texture of a golf ball affect the car's gas mileage? So the independent variable in this would be the surface of the car is either dimple or no dimple. That's what we are changing. Now, what's the dependent variable of the experiment? That's the gas mileage. That is what is being measured. And some constant variables would be like the type of car, the speed of the car, the driver, the road conditions, like the weight of the car. Everything needs to be the same except for the independent variable, which is what we're changing, or the dependent variable, which is what we are measuring. So we put this to the test by asking this question: do the actions of flipping and spinning a penny affect the percentages of which side the penny lands? And we did this with penny for your thoughts. So But in the lab, you're asked to identify the independent variable, dependent variable, and three constant variables of the experiment. And we've already done this before. That was a couple of minutes ago. We identified those variables. Now, it asks you to identify if this statement is a scientific claim. Spinning a penny on the table will cause it to land heads up more than if the penny was flipped. Well, is there a test for wrongness? Think about that. Make a hypothesis. So write your hypothesis. What do you think? This is an educated guess. Be specific as possible. Remember the rules for a good hypothesis. Now, then in this lab, a penny is flipped 50 times, and the same person is doing the flipping. The penny should go up about 1 foot. The penny should always start heads up and catch the penny in the other hand, but do not flip it to the other hand. Record the data. Then spin the same or that similar penny on the table 25 times. Make sure the same person is doing the spinning. The penny should spin for at least 5 seconds. So then you record that data. So let's look at this. Now, this researcher, he deduced that the Lincoln's head has a lot more mass than the Lincoln Memorial on the reverse side, and it would throw off the center of gravity, and it should fall down with the heads more down than tails, so it should come up tails more. Well, in the class, we spun penny 825 times. Now, notice that when you're spinning, yes, it did come up head or it did come up tails when spinning a little bit more, but it wasn't the 80% that was predicted. Now, this researcher goes on and says that, well, because pennies pick up dirt and oil, that would sort of balance out on both sides. But if you have a new penny, then it should be about 80% landing tails. So this is one of the errors that we talked about with the penny. So it could be considered a systematic error because it is like the equipment that we're using. It is a defect in that equipment. All right. So look at your hypothesis, and based on this data, was your hypothesis wrong? Was there a significant difference in the percentage when comparing flipping a penny to spinning a penny? Now, these are going to be different data than what you have. So look at your data and decide whether your hypothesis was wrong or not. Now, if so, claim why do you think that would be? So it seems to be about 50-50. And based on what we just learned, I would say because even though Lincoln's head is a little bit heavier, I would say because those pennies weren't oily, or they were oily and they were like degraded, that would balance out the center of gravity, and it would come out about 50-50. Now we could test this for wrongness. We could clean those pennies with vinegar and salt and make them nice and shiny and new, and then try this experiment again and see if that affects the results. So random errors that could have been in this experiment. So the random errors, flipping a coin is just a random error. It's because it's a random error based on our ignorance because we don't know the initial conditions. It's your inability to take the same measurement twice. If you could do this experiment the exact same way, if you flip the penny the exact same way, it would come up the same side every single time. And in fact, people have built machines that can do this. If I put this coin heads up, it'll flip it. It'll always come up heads up 100% of the time. So just the act of flipping and spinning a penny, those are random errors. Now, the random errors are going to affect your precision, your inability to do the same measurement the same way. We're hitting darts differently every single time. And what could be done to mitigate the random error? Well, not really much. I mean, we could make a machine that could flip a coin the exact same way every time, but there's not much that we could do. Now, systematic errors are defaults in the measuring equipment. I would say that there weren't really any systematic errors in this experiment. Maybe what you could do is you could say because the pennies were corroded and oily, that would be a defect in our instrument. But like we really didn't have any measuring instruments in this lab. So another question we would ask if a nickel is flipped onto a flat surface, what are the odds it will land on the edge? So the probability of an American nickel landing on edge if tossed onto a flat surface is approximately 1 in 6,000 tosses. Let's put this to the test as a class. Flip the nickel on the table as a group for a total of 200 times. If every group in all classes do this, and as a class we will have over 6,000 tosses. Odds are that one of those tosses will land on the side. Record the results in the table. So as a class, in all my classes, all the groups, flipping a nickel onto a flat surface over 200 times, notice that as a class we got 5,736 flips. Now notice that there was one that landed on the side, and you can see that picture right down there. That is the nickel that just happened to land on its side. So it's about 50-50 with heads or tails, but there is a very, very small percentage, a 1 in about 6,000 chance that it'll land on its side. So there was another experiment being run on the side. Does the side of the coin that is initially facing up affect the percentage of which side the coin lands? So let's look at an example, right? So this is a claim. The side of the coin that is initially facing up will land with a higher percentage than the side facing down. Is this a scientific claim? Why or why not? Yes, it is a scientific claim because there is a test for wrongness. So and we did test this. So let's look at the independent variable. So does the side of the coin that is initially facing up affect the percentage on which side the coin lands? Well, the independent variable, that is the side that is initially facing up. That's what we are changing. Well, we're not really changing it, but that's what we're testing. We're testing to see if that side that is up will affect that percentage. So let's look at that dependent variable, what we are measuring in this experiment. And the dependent variable is the percentage of landing on each side of the coin. So that's what we're measuring. We're tallying it up and calculating the percentage. Now, the constant variables are what remains constant, what we keep fixed. So does the side of the coin that is initially facing up affect the percentage on which side the coin lands? Well, you probably want to keep the person flipping the penny the same, the height the penny that is flipped, the side facing up at the beginning. I know that was the independent variable, but that's what we are manipulating. But we want to make sure that it's the same side every single time. If we do heads, we want to make sure heads is facing up. If we do tails, we want to make sure tails is facing up every single time. And you want to keep the flip the same. So whether you flip it over at the end, and especially the coin, you want to keep the coin the same. Everything needs to be the same except the independent variable, which is what you are changing, what you are manipulating, and the dependent variable, which is what you are measuring. Right, so these are the results. So all in all, in all of my classes, we flipped a penny 1,700 times with heads facing up every single time. Now, what do you notice about the percentages? Well, yes, if you look here, we started every single one of these 1,700 flips heads up. Now, notice that, yeah, it came up 52.65% of the time it landed heads up. So there was a slight advantage to the side that was up, and that's because well, if you start heads up, it's always going to be facing heads up. Just more time in the air, it's going to be facing heads up than tails up. So, was this claim right? Why or why not? Well, no. Remember, it's in science, nothing is right. You're just not wrong. So there could be another experiment, and maybe next time I'll start tails facing up. So that could be an example where we could do this again. But remember, in science, you're never right, you're just not wrong. So, as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.